Okay, today we're going to talk about Chapter 3, Section 2. Before we go on to Chapter 3, Section 2, I would like you to take a second right now and review the concepts. So, 1, you should be able to pause this video after these questions and answer these. 1, what is Newton's first law of motion? 2, what is Newton's second law of motion? And make sure that you can give practical examples of both Newton's second law and first law of motion. Okay, today we're going to talk about Section 2. Section 2 is going to talk about Newton's second law of motion and applying it to what we know as gravity. So Newton's second law of motion, the law of acceleration, is force is equal to mass times acceleration. So let's talk about gravity. Gravity is really an attractive force between two objects. Now, any two objects in the universe have to have a large mass and a distance between each other. Okay. So as the mass increases, the distance will then decrease, such as an object that is very small coming in contact with the Earth, which is very large. The mass of the Earth is going to pull that object into it. And so if the mass of either of these objects increases, the gravitational force between them will also increase. Also, distance will, as your distance decreases, you'll see a mass increase with some of those objects as well. Now, if the objects are close together, the gravitational force between them will start to increase. It will actually pull them in towards each other. So objects that will come in contact with Earth that have a much smaller mass than Earth, such as a meteor, the distance will start to decrease between the Earth and the meteor until the meteor will actually smash into the Earth, increasing the Earth's overall mass. And so here's what we know about gravity. Who experiences more gravity, the astronaut or the politician? Okay, so obviously there's less distance, and which means we have the astronaut experiencing less gravitational pull than the politician, because he's floating above the Earth where the politician is actually on the Earth. And so you can see the moon out there. The astronaut is actually going to have greater gravity is going to affect the astronaut more than the moon because of the distance between them. Okay, gravity is one of four basic forces. We've talked about these before last semester. And so the other ones are electromagnetic force, which we're going to talk about in a couple chapters, and strong nuclear force and weak nuclear force. Now, you can pause the video right now and you can go over strong nuclear force and weak nuclear force because we've already talked about those last semester. You should have remembered or answered as a group that the strong nuclear force is found in the nucleus, holding the protons and neutrons closely together, and the weak nuclear force is holding the electrons to that nucleus. So that's a good review for this. And so Isaac Newton was the first man to come up with the law of gravity. Ironically, they say an apple fell on his head, and that's how he discovered gravity, but not quite the same. We do know that the further the Earth, you travel from Earth, the less gravitational pull that you have on Earth. And there becomes a point where the range of gravity actually changes, and you will not be able to be pulled back to Earth's surface by Earth's gravity because you're too far away. And so according to the universal law of gravitation, this is a law, which means it doesn't change ever. The gravitational force between two masses decreases rapidly as the distance between the masses increases. So you don't have a great enough pull the further away that you get from another object. No matter how far apart two objects, the gravitational force between them will never completely be zero. One object will always have some gravitational pull over the other object. We don't ever see a zeroing out of these objects. And this is because the gravitational force between the two objects will never completely disappear, and it just becomes a very long-range force, such as we have Pluto, a dwarf planet circling the sun. The sun's still acting on it even though Pluto's super far away. And if you've read the news now, you know that there's a ninth planet that they finally discovered, unknown name at this point, but we know that it doesn't disappear, that this gravitational pull will keep acting on these planets as long as the sun is there. It doesn't matter how far away they get. Okay, so let's talk about the Earth's gravitational acceleration. So when we start talking about this, we have a thing called gravity, and gravity for Earth is 9.8 meters per second squared. And so that's how fast things are being pulled to the Earth's surface. So the force of gravity is actually mass times acceleration. So our acceleration is 9.8 meters per second. Make sure you have that on your note card. Gravity is one of those things that you should just know. It's not going to be in every word equation. Okay, so when all forces except for gravity are acting on an object can be said to be in free fall. Now, this doesn't really happen because we have this thing called air resistance that is occurring on most objects, and they'll reach a terminal velocity like we talked about last chapter. However, in a perfect scenario, something can free fall and not have to worry about any other forces acting on it. So, the acceleration, by the way, for gravity is always given the symbol g, and we have that there. So, here we go. So, the closer to Earth's surface, the acceleration will have a free fall of 9.8 meters per second squared. This is in Earth's biosphere, or a basic atmosphere, the closest level before the stratosphere. This acceleration is always called g, or gravity. By Newton's second law of motion, Earth's force, or free fall, of the objects is acceleration of gravity. So when we have this equation, Earth's force of gravity is equal to the mass times acceleration. So whatever the mass of that object is in kilograms times 9.8 meters per second. We also call this weight. Remember, your mass is not the same as your weight. Your weight is your mass times gravity. Because gravity is acting on us, you will not have the same weight on one planet compared to the next. As the lab that you guys did last section, you kind of already know that. The equation at the bottom of this PowerPoint, you can in the blue box, you can put onto your equation sheets so that you can have that for your test. So weight is measured always in newtons, mass in kilograms, and gravity, or g, is meters per second. So mass always depends on, mass is always the same in kilograms, and weight depends on gravity. So that's really the difference. Note, our scales take gravity out, so we're actually measuring a mass, where weight is that newtons, so they're different labels. Don't put weight as pounds. lbs is not the label for weight. So gravity. Where would you weigh more, Earth or Jupiter? You can pause the video and kind of answer that question now. Well, it'd be Jupiter. And if you look at the table in your book, I believe, yep, it's on page 78. You can look at that and it'll help you out a little bit. So Jupiter, because the mass is greater, the greater the mass, the greater the gravity, the greater your weight. So you could actually calculate how much you would weigh on Jupiter based on your Jupiter's gravity. So weight and mass. They're not the same, you guys. This is a misconception that weight and mass are the same. And they really are not. Weight is actually a force being applied to your mass. And so I can't stress that enough, because we're not just going to talk about weight in this chapter. It talks about it in the next few chapters. So you really need to understand that weight is the amount of force being applied to your mass. And mass is just a measure of the amount of matter that you have. And so when we start looking at this, they are related. But as your weight increases, your mass will also increase, because your gravitational pull, or the gravitational force, usually will stay the same. Unless you change planets, and then that would be different. Now, weight is dependent upon the gravitational force of an object. So as you go from one planet to the next, such as in this table right here, you are going to see that there's going to be a different weight for each of those objects. And so you would vary your weight, even though your mass didn't change, the gravitational pull changed. And so because that gravitational pull changes, then your weight will also change. This is also why an astronaut on the moon can bounce and almost fly off the planet. Where on Earth, you just walks across the floor, there's no big deal. One of the things you need to worry about when we talk about gravity and how this changes, why do astronauts need to work out in space? And even if they work out twice as much as what they do on Earth, why do they actually lose muscle mass? You can pause that video and kind of discuss that question. So they actually lose muscle mass because you build muscles based on the amount of force being applied to that specific area. And then you start to increase the mass of the muscle. No matter how much you lift in space, the weight is not the same on Earth. And so you're actually not able to build up the muscle mass because you don't have the same weight being applied to it. So the gravitational pull doesn't allow you to create that. So let's talk about weightlessness and free fall. So, where would you find a weightless environment? Well, we would find a weightless environment in space, typically. And so, if you've probably seen some pictures of astronauts and stuff floating around in the space shuttle, and they're experiencing this weightlessness. However, if we would show a scale, they have an upward force being exerted on them or on their weight. And so now suppose you're standing on a scale and the elevator is falling, such as we have here. As you're on that scale, you're in a free fall. You no longer would have a push down on the scale. So would you weigh 0? Because you're not having that same push. Even though the force of gravity hasn't changed, we're kind of making that free fall into a place where we have no gravitational pull, or the gravitational force isn't influencing the object. And the sensation of weightlessness is actually produced when an object and its surroundings are in free fall, and the object is not really weightless, but has weight still to it. So, floating in space, a space shuttle can orbit in a free fall pattern. And you can see the straight down motion. Everything is orbiting around or falling around the Earth's rotation, but everything's going around the same weight, or same rate around the planet.